Hey, everybody.
Hello.
All right, let's get started. Or let's wait a few minutes, actually. All right, let's wait a couple minutes in case people show up, although a lot of people are here, but just in case. Plus, because I have to make a phone call. And then we'll get started. Okay. All right. So yeah, the plan was that I was going to talk about cycle handling, I think, right? Yes. So I guess the first thing is, I don't know whether, was everybody here in the, or has seen the call that we did the last time? Has anyone not been part of that? Okay. So let me share my screen. And yeah, the plan is to post this to YouTube, by the way. So if that makes you uncomfortable, sorry. Just FYI. Feel free to ask questions via private message or something if you prefer. So, right. So let's see. What I wanted to talk about was the existing cycle handling. And the reason was partly, well, because it's complicated, but also because I expect to be extending it to handle fixed point cycles or other kinds of cycles. So let me show it. Let me just start with, like, as a user, how sort of history of cycle handling in Salsa or something. I mean, I think when Salsa first started, it was really before it was Salsa. It's more the Rust compiler. And there we have realized that, of course, when you get in a cycle, it's not very clear what you should do. So you're doing, everyone knows what I mean by cycle, I guess. You're doing a query, and in the older sites, yeah, db.query A, and executing that query leads to db.query B, which then leads again to db.query A. And now you have this problem of, like, how do you do that? What's the answer for A, given that you're already computing A? So what we did in the compiler is we just panic, right? Just can't handle it. And we print out a, you may have encountered it if you've written enough Rust, we print out a sort of annoying error message giving you a little stack trace, and hopefully you can kind of figure out what you did wrong. What Salsa tries to do is give a little more ability to recover. The idea is that you can tag some of your queries with this, I think it's called Salsa recover attribute. Let's take a look. Let's look at a test. So here's one of these tests, and we got this this cycle A query, and you see that it's tagged with this attribute that gives a function called recover A. And so the idea is, if there should be a cycle, so you tag a query with salsa recover, right? So if there should be a cycle that involves Q, so that it's not an error in Salsa right now. Instead, you execute some function which will yield a result, and you use that instead. And so you can kind of break the cycle this way. So in this example, and it's not an error from the point of view of Salsa, I mean, right? So in this example, the result of this query is a result. So the recovery function just supplies an error ERR variant, and the normal function, wherever it is, here, well, it does some stuff. What does it do? It calls A invokes. Oh, right. So it has this is kind of a testing harness, so it can get redirected, but cycle A calls whatever this variable says to call, which might or might not lead back to cycle A, but ultimately it's going to return OK of unit, right? So that way in the test, but either way, from Salsa's point of view, the query succeeded and we have a result. We have some value of result error to return. And you can see here that in this recovery function, it gets given an argument of type cycle. So that argument is defined here somewhere. I don't remember, maybe in runtime. Oh no, it's at the crate level. Okay.
Nico is apparently having some connection issues, but he's rebooting his machine now.
Hello, sorry, I don't know what's going on with my computer, but it decided to not have internet for a little while. But now it does. Let me try to reopen this HackMD I was poking on. Yeah, so what I was going to say was, if I remember, that the cycle, when it's involved in a cycle, it's going to return whatever value that function returns. And the cycle is kind of broken at that point because we just abort, we just sort of abort what the query was doing. And so now there's no longer an edge from that query to whatever edge came after it, and therefore there's no cycle. Okay, does that all make sense? Any questions on that so far? Oh, I remember I was going to show you what cycle participants looked like. It's not very important, but it's just a shared vec of database key indices. If you remember, a database key index was the thing that like has, it's like an integer that uniquely identifies a query. Okay.
Is this mostly intended for error recovery, like not panicking, but not it doesn't do anything for fixed point computation and so on right now.
Yeah, that's right. So it's just for error recovery. An interesting example that Matt Clyde gave of how you could use this, for example, is you might have like, oh, now I'm forgetting the details. Well, you could have a cycle that sort of says, like, I will build all the modules is one query, and this one says like, build module A, build module B, build module C, and maybe one of these, for some reason or another, requires you to build all the modules. Then what would happen if and then say that build module has the salsa recover attribute, then what would happen is we would use the recover flag or function here. And so you would wind, and maybe this returns, let's say, result of modular error, and this returns a vec of result of modular error. You would wind up with a vector with like OK module A, OK module B, and then error, right? Usually, though, you don't actually use a result type. You just have sort of some kind of error variant in your type to indicate that a user error was encountered, right? That's the idea. Okay, so let's see, how does this actually manifest? Well, I'm going to pull up that. I'm going to pull up that chart because it will be helpful. There we go. So if you remember, this is kind of the overall algorithm. And when we're executing a query, we start by looking if we have a result. So in this case, we're going to say, no, we don't have a memoized result. Then we go and claim this entry in the sync map. And this is kind of interesting because cycles can actually happen in two ways. Like if the easy case is the cycle is all contained on one processing thread. In that case, you can just look up the stack to find all the participants. And there's kind of no real work to do. We'll go back to it, but there's a little work, but not too much. But the harder case is cycles across threads. So what can happen is that you have one thread, let's call it thread A, is executing like query 1, query 2, which in turn executes query 2, which in turn executes query 3, and then which in turn executes query 4. But meanwhile, thread B is executing, or let's do this, A1, A2, A3, B, B1 or B2. Say B might be in the middle of doing some work, right? And now what would normally happen is thread A will block waiting for B2 to finish. But maybe B2 then goes to execute some A query like A3, right? And so now we have a cycle. Okay. Did you just lose me for a little while?
Yeah.
Yep.
Yeah,
What's going on? Well, I'm back now, apparently. What did I last say? I was talking about cycles across threads. Did that come through?
Yes.
Yeah, you were just about to get into that.
Okay, cool. So I don't know what is happening with my internet, but anyway, so let's find the code where it happens. That's what I wanted to do. I don't have a pretty diagram for this one. so what winds up happening is we go into, here it is, the runtime. You know what I should do is get this in VS Code. I think that will make me happier. But is there some way to like go into a VS Code session just from
You press
dot? Okay, that would be cool. Let's see if this works. Does it support Rust Analyzer? Probably not.
Last time I checked, it didn't.
Too bad. That would be even cooler. Okay. Let's see. So let me try to remember where it is. Not unblock cycle and maybe throw. Here, block on or unwind. So this function gets called when we detect a cycle, right? So we come through and we say, there's another thread that's already active. Then we call block on or unwind, and that let me see, where's that? That's under derived, execute, no, fetch, maybe. Fetch cold, sync map.claim. Oh, of course, this doesn't do what I want. I want to jump to definition, but here we go. Yeah, so if we'll go to this sync map and we'll look and see if there's already an entry. And if there is already an entry, then we're going to flag something there. I'll come back to that later. And we're going to call this block on or unwind. And so the job of this is basically to say, either I need to wait until that query completes, or in the case of a cycle, I need to unwind. And so what is that about? The way we handle cycles is that we use the unwind machinery because it's really convenient. So the idea is that if you do detect a cycle, you're going to start unwinding and peeling off queries as you go up until you get out of the cycle, and then you'll resume execution. And so the block on or unwind, either blocks on it or it unwinds in the case of a cycle. And now we can pop back over to there and see what it does. We use this dependency graph. And so the idea is that we have a little shared data structure in the runtime that represents a graph of threads. So let's say we haven't executed this yet. Right? When we get to the query B2, what's going to happen here is we're going to get a lock on the dependency graph, which is shared across all threads. And we're going to insert the edge A to B, right? And I mean the thread here. So we only have one edge for the whole thread because that's all you need. The thread is blocked. So that happens here. There's a little map that says the runtime ID is identifying the thread. So from the runtime ID, there's some edge, and this edge gives it a little interesting information. So blocked on ID and blocked on key, this is who am I blocked on and what are they doing? So in this case, right, we called query B2. So we would insert an edge with kind of, depending how you want to think about it, the blocked on ID would be B, that's the thread. The blocked on key would be the name of the query. So that's essentially B2, or the query and its arguments, the database key index. And then this field is kind of interesting, stack. So what is that? What that is that's actually this stack. That's the stack of the thread that's blocked. So we move ownership of that stack into this data structure, and we put a none in its place in the color. I'll show you that later, why we do that. But it has the nice advantage that anytime that a query is stalled and blocked, waiting for something else to finish, the entire query stack for that thread is available under this lock, right? And there's no contention for it. And then finally, we have this condition variable. So what this does is, this is a way for people to wake us up. So if, in the case of query B2, we're going to wait until B2 finishes. So we're going to block on that condition variable. Let me see, where's the code? To block on. So we'll add an edge in the graph. I'll come back to this in 1 second. Then we will do a little loop where we just kind of wait for that. We either check if there's something in my set of results, and if there's not, then I'm going to wait on the convar until somebody signals it, and then I'll try again to see if I can get some result. Don't remember where this even, what is me? Me is the guard, okay. That makes sense so far? Okay, so if we go, me is actually, so in order to call this block on function, it's not a regular method. It has to be called with a mutex guard, which means you can only call it when you've actually locked the dependency graph. I forget why it's that way, but it's probably so I can do more than one operation while the lock is held. But so in here, we kind of store this. The purpose of this wait results is just when someone's blocked, to unblock them, so what will happen is when, let's go through the non-cycle case yet. Right, so what happens so far when we go through is B2 adds itself into the graph, and it essentially waits on the convar. In that case, query B3, let's say it just completes, and then query B2 completes. What happens now? So what happens is it detects, and I'll explain how in a second, that someone is waiting for, is blocked on this result. And then because that's true, it calls the dependence, the unblock method on the runtime. So that's here. It's going to call actually this one, unblock runtimes blocked on. So it's saying, let's see, yeah. So it's basically saying, hey, I just finished B2. So anybody who was waiting for B2, they can wake up now and try again. They should find a memoized result in the cache. And actually, there's this result, which we can ignore for now, but that essentially says, did you complete normally or not? So in this case, it would say, it'll look up in, there's a reverse map. It'll find out, oh, okay, thread A is blocked on B2. So it's going to push into this map the value that thread A is going to get, and then it calls notify1 to wake up thread A. I'm jumping a little fast, but does that make sense? Okay. This will push the result into the wait results map, and then call notify1 on the convar, which wakes up thread A. So thread A wakes up, reads from the wait results map, and completes normally. And if we go back to our little cycle, we'll see that if it was already claimed, we were going to block. When it completes normally, we're just going to loop back and start this whole process over again. Right. So this time, though, we expect something to be in the map. So we'll take this fast path. So good. So far, so good. It's okay if it's not. Okay. So what happens in this cycle case? If we unwind the stack, or when we call block on, right? So suppose, going back to this example, thread A was executing just like we said. I'm gonna maybe change this to slightly different notation to interleave the activity of the threads. So, right, so thread A was executing and wound up invoking thread B. And sometime intermingled with that, let's say, thread B did query B1, thread B did query B2, right? So now query B2 is already started, so we're going to block on it. And now thread B comes along, and let's say that query B2 invokes the query A2. Right, so this is going to proceed the same way. It says, oh, it's already got an entry in the synchronization map. So it's going to get a lock on the database graph, and it's going to call block on or unwind, or whatever that function was called, saying, here it is, right? Saying I need to wait until A2 is finished, which will acquire the lock. And while it has the lock, it calls this depends on, and all that does is do a simple, it goes the other way, calls block on or unwind, which acquires the lock, which walks the graph from, walks the dependency graph between runtimes. So what we're saying is we call block on or unwind with thread A or A2. So the question is we're going to block on a query that's inside thread A. So is thread A blocked on the current thread B? If so, we have a cycle. Right? And in this case, we're going to find yes, it is. So then we're going to call unblock cycle and maybe throw. And this is where all that recovery mechanism starts to come into play, because now we know there's a cycle, so we have to do something for us to execute. Let me see if I can find unblock cycle and maybe throw. Where's that? Oh, it's in the, sorry, it's not in the dependency graph, it's up here. Okay. So this is unblock cycle and maybe throw. What does it do? Well, the first thing it does, let me see if I can remember. Right, first thing it does is it tries to enumerate all of the participants in the cycle, right? And this is where those stacks start to be really useful. So the fact that we have ownership, that any thread that's blocked, we have their full stack available to us, means we can kind of do this in a relatively straightforward way. So we have this function for each cycle participant. Oops. And it's here. And essentially it walks that cycle and invokes this callback on each one. Right? And there's a little drawing here of this, how it works. But you can kind of imagine we're starting from, let's say, right, let's say here, we'll use this diagram. So we're trying to add this cycle, but we failed because we found B depended on C, which in turn depended on us. So what we're going to do is we're going to start from that place and go down the stack until we get to the bottom. And then we'll go over to the other thread and go down the stack. And eventually, repeating that process, we'll reach ourselves. Right? We'll reach our own thread again. That's what this code does. So each turn of this loop goes to a different thread. So it starts on thread B. It gets a chunk of the stack, basically saying, give me everything. This prefix is iterate, skip past all the things up until the one we're looking for on the stack, and then starting from the prefix, take a slice of the stack and call the closure. So the closure will get called once with these two entries, and then again with these two. And then in the final turn of the loop, we have we handle the case of the initiating stack. These are a little different because thread A is not actually blocked. So its stack doesn't live in the dependency graph yet, because we couldn't. Thread B and C, their stacks live in the dependency graph. So that's why when it says copy in the results, that's what it's talking about, is we pass in this stack as an argument, but these ones are in the data structure already. Any questions on that? Oh, I have a
What is
message.
the closure there?
That's a good question. The closure will depend. We call this function a number of times and do different things on each cycle participant. So this is kind of a building block for the rest of the algorithm, which I'm about to go through. So like the very first thing we do is we just find all the cycle participants and put them in one big long flat vector. So in that case, the query, the closure takes in the active queries, that's what AQS stands for, iterates through them and pushes them. Oh yeah, ignore that for a second, I'll come back to that. Pushes them into this vector. You can ignore this line for a second. Pushes them into the vector so that when we're done, we have this vector that's going to contain everything that we needed, right? So let's see. Can I like, no, I probably can't. So step one, we identify the cycle participants. So we would get the vector. In this case, we would say, okay, we're trying to call A2. So we'll start there. We'll get A2, A3, and then we'll get called on B because A3 called B2. So we'll have B2 and B3. And then we do this rotation thing. So here the deal is we want everything to be deterministic, and depending on what order the user invoked the queries in, you would actually get different orderings in the cycle, even though everything else is deterministic, and that kind of would mess things up. So we do this rotation. So if you imagine, like in this case, we started, because of the thread ordering, we wound up detecting the cycle here, and so A2 was first. But if thread B had started first, we might have started the cycle or detected the cycle at this point, in which case we would have gotten essentially, we would have started with B and then gone to A, right? And we don't want that variation. We want to identify the cycle as one in the same way, no matter where it starts from. So what we do is we find the minimum one by, these are all dependency key indexes, right? So they're just a big number. It's a little bit of an arbitrary number, but it's still a consistent number that will be the same across all revisions, or across all revisions where no changes have occurred. And so we just find the minimum one, and then we rotate it about this. So in this case, whichever happens to have a lower dependency key index, we would sort of transmute it to the other one. Because you can kind of start the cycle from any point in this list, right? Okay. So now we have all the cycle participants, and that is that cycle data structure we're going to give to the recovery function later on. Then, yeah, I don't remember what this is for, so we'll come back to that. But then what we do is we go through that list of all the participants, and we mark the ones. We have a little marking system by setting aq.cycle that have recovery set up. So if, in this case, let's say that the query, I don't know which one, let's say that suppose B2 has recovery, right? In that case, we would set sort of, for each of these active queries, there's kind of a little stack frame record for it. So we would set the cycle flag to true, and everywhere else, the cycle flag is none. Every other stack frame. And remember that the stack frames are either on the current thread or we have ownership of them because they're in the dependency graph. So that's what this code does. And what it actually does is, let's see, any frames that come after them. Yeah, I don't remember why it does that, but we'll come back to it because we'll find out. Unblock every thread that is cycle recovery. Yeah, okay. So this is where it gets a little bit interesting. Now we have these threads, and they're blocked waiting for that conditional variable to get signaled, right? And so what we're going to do is we're actually going to wake up any thread that has some query which has recovery. We're going to wake it up. So the idea is that all the threads that have recovery are kind of simultaneously set to recover. So they're going to skip all the rest of the work they were doing and just execute that recovery. So they don't have any more, they don't need to block because they're no longer waiting for the result that they were waiting for. So then we wake up the threads with recovery. So in this case, that's our own thread, which doesn't really need to be awoken. So there's a sort of special case to handle that. So let's actually just change this. Suppose that A2 had recovery. Be more interesting. So in this case, we're in thread B right now. So we wake up thread A, and actually we would set A3.cycle also. We wake up thread A, and we give it a wait result cycle. So I mentioned earlier that when you unblock, you actually set this wait result. The wait result tells you, did you get woken up kind of normally, or did you get woken up because a cycle was detected? So where is wait result? It's here. No, it's from super. Okay. Yeah. So here's the wait result, right? The reasons you can finish, the reasons that you might, that a query may have terminated. One is it completed normally. One is that it had some other panic that we don't know about, or because it had a cycle. Those are the three ways for a query to complete. And so if we go over into execute, what's going to happen now is, where are we? We just woke up thread A, right? So thread A was in the middle of it was executing A3, and it was trying to manage B2, like get the synchronization map for B2. So that will come here, which calls block on or unwind, which when we wake it up, no, I'm trying to remember how this works. It's going to panic somewhere, and it's going to start to unwind. Oops. So it's going to unwind through these different frames, and that gets caught here. So this is what's happening here is this is where we're actually calling into your code, like into the callback to run the query itself. And it catches an unwind that resulted from a cycle, or rather, I think it just catches any unwind. Or is it only a cycle one? I guess it's only a cycle one. Right, yeah. Yeah, so it catches an unwind that results from a cycle, which it does by checking what value was thrown. And if there was a cycle, it checks the cycle strategy. And if fallback is set, then it's going to call your fallback function and proceed normally, as if it finished normally. So what will happen here is thread A was blocked on B2. B2 is going to panic with this cycle as its value, which will unwind to A3. A3 will catch the cycle, but say, oh, I don't have fallback. So it's going to rethrow the panic and just keep unwinding. So A3 unwinds and goes back up thread A and goes to A2, which catches the unwind, but it does have recovery. So it executes. This is exactly the same path. It's going to memoize so we unwind query A3, we unwind query A2, we catch the unwind, execute the recovery. This gives us a value, V for A2, let's say, which we store as normal, and just resume executing. So query A1 completes, right? That's what happens to thread A. Query A1 completes with this value V, and we're all done. So we recovered from the cycle on thread A. The question you might ask then is, well, what happens to thread B? Because thread B was actually the one that initiated this whole thing. It was about to go to block on query A2 when it found there was a cycle. So it couldn't actually block on A2. But now we woke up thread A. So what do we do? Runtime. I don't know. So let's read the code. I think I know. Unblock cycle. Yeah, so what we're going to do, it's actually an interesting thing, is it depends on whether we ourselves have cycle recovery within our stack, within thread B or not. In this case, there is no cycle recovery. So actually what we want to do is that's going to be this path where others recovered, is we just return normally and pretend there was no cycle to begin with, right? So we were checking here, we were in this code, we said, did thread A depend on us? Yes. Then we called unblock cycle. Well, that woke thread A up. So thread A doesn't depend on us anymore. So now we can just go ahead and block on thread A just like we would have done before. So we're going to block on thread A. And actually, this all occurs under the lock. So thread A didn't really wake up yet. This will have happened before thread A, before the semaphore wakes up. But it's ready to wake up. It's waiting to wake up. And we're going to add a dependency, B to A, and block. So that's what thread B does. And meanwhile, and then it releases the lock, right? And meanwhile, thread A acquires the lock, sees that a cycle occurred, panics, or initiates unwind. Let's say it is a panic, but a controlled one, which will unwind query to, which will unwind this, which will catch the unwind, execute the recovery, and resume executing. And now at that point, that's just like any other time that a query completes. So whenever a query completes, we check if somebody's waiting. So it'll notify people waiting on A2, which means thread B will wake up and resume executing. And it will read from the memo map and see the value V. So at that point, from the point of view of thread B, even though there was a cycle, it's like there wasn't, because query A2 had recovery. And so we just get whatever value was there. Okay, that's the algorithm. And we're running short on time, so let me open the floor and see if it made any sense to anyone. And if not, what might help it make sense? So I thought this was so beautifully documented, but as I read the code, I felt it could be better.
I'm a little unclear on the other case where what happens if I understand that the case where you unblock the other thread, you run recovery on that one, and then you sort of resume the first thread as normal. What is the use case for having recovery on both threads?
Okay, so well, there's two questions in that, I guess. The use case for it is kind of, it could happen. Like you can add recovery to any query, and so we have to be ready for that. But what do we do in that case is that we will first of all, we'll wake up every thread that has recovery somewhere. We're going to wake up so that that recovery can execute. And actually, there's a little bit of a subtlety that I forgot, but I'll come back to it in a second. Every thread that has recovery somewhere, we're going to wake up so that it can execute. And that includes the current thread. So if the current thread has recovery, it doesn't need to be woken up, but it won't go into a blocking state either. What it will do is it will throw the cycle itself. And so if, for example, query B2 and A2 both had recovery. So suppose A2, B2 both have recovery. Then everything is pretty much the same, except here we don't add a dependency. Instead, we initiate unwinding, which means thread B will unwind B3, it'll unwind B2, it'll see that we have recovery and execute the recovery function, storing the result as normal. And then, of course, thread A is independently executing. So somewhere along the line, it will unwind A3 and so on, just as before. And so now we wind up with two recovery values stored, one for A2 and one for B2. Did that answer your question?
I think so. And the use case is just then I guess that you would want both queries to return an error, say, if there was a cycle anywhere, because they both participated in it.
Yes, we want the guarantee that if your query participates in a cycle and it has, there's a lot of subtle determinism traps here. So we want the guarantee that if your query participates in a cycle and it has recovery, you will see the recovery value. Then we'll see the recovery value. And that's true no matter what, sort of true no matter where the cycle started. And that's the part I realized I didn't cover. So like if you're not a little bit careful, you can, if you can kind of get in non-deterministic results where if the query were to start from one place, then you would see the recovery value from one, or if the cycle started from one place, you would see one of the recovery values, but not the other ones. And then if it starts from a different place, you see different recovery values. And then that's really bad because once you have non-deterministic results, the whole incremental algorithm breaks down and stops working. So what we actually do is there's a little bit of a trick, because actually the way I described the algorithm to you, you could totally have this problem. In particular, what if both, so like what if A1 and A2 had recovery set? The way I said, we're going to unwind until we get to a frame that has recovery. That would mean that A1 would just resume executing as normal. And that would be bad because now A1 doesn't see the recovery value, but A2 does. But if we had started the query from some other spot such that, like say if we started executing A2 first, then A1 would have been the top of the stack and A1 would have had its recovery value and not A2. So that's not good. So what we do, that's actually why we, to accommodate this, that's why we mark, I said that we mark every cycle participant that has recovery set along with any frames that come after them. And we do that by setting this cycle field to true in the stack frame. And that means that even if something recovers from a cycle, if there is a stack frame on top of it in the stack that has recovery set, you have that marking, right? And the idea is if you have that marking, we don't want to finish running your function. We want you to panic so that the recovery that's on top of you in the stack, or underneath you, I guess, depending on your point of view, but that's blocked on you in the stack, can execute. So what we'll do is, in this case, we would execute A2 recovery and store it in the memoized map. But then there's an interesting spot in the fetch function. So, or maybe it's the execute, you know, where is it? Somewhere, I don't remember exactly where. We check this field. Is it fetch? Compute value, execute. Well, I'm not sure where, but if you follow along, there's some there's some code. So the code for A1 had invoked like the A2 function, right? And we check as we pop the stack frame for A2 from the runtime, if this, oh, that's where it is, that's right. If the cycle flag is set, if so, we initiate unwinding again. So actually it's in the runtime here. Remember, we maintain a stack of all the queries that are on this stack, on this thread. And I told you that ownership of that stack moves from the thread into the dependency graph and back. That's why it's a ref cell option, so that you can swap none when you're blocked and then take it back when you're not. And in here, we can push things on the stack. And then at the very end, this very long cycle name, when the query that's on the stack, like A1, invokes another query, we want to record the fact that A1 invoked A2. So we want to add A2 as a dependency of A1, right? And that's what here. At that point, that's where we check, oh, look, actually, that was executing, something about executing A1 led me to be a participant in a cycle. I'm going to throw this error. So in some sense, A1, when A1 calls A2, A2 finishes and recovers and returns normally. From A2's point of view, everything is fine. But then A1 says, actually, I need to not do the rest of my work because there's a recovery either in me or in someone else that is blocked on me. So I'm going to just panic and skip the rest of my function body. And so that will unwind. In this case, A1's function body will catch it, and then A1, the logic that started A1 executing, will recover. And they'll both end up storing the recovery. That makes sense? That took me a while to get right, if I remember, because it could be that A2 has recovery and everything on top of it, or everything blocked on it in the stack, just wants to use that recovery value. So it sort of depends on what's A2's behavior is independent of what is blocked on it. That makes sense. Okay. Well, we're at time. I hope this was helpful. I think what comes next in terms of this Salsa maintainers lecture series, I mean, I've kind of explained everything that's in the algorithms now. I think what's probably the next set is, first of all, I want to start coming up with, actual bugs to fix and work items. And so we can chat a little on Zulip, but one thing is, well, one obvious problem is there's some slowdowns from Rust Analyzer that have to be analyzed. But also, I think various enhancements and things, and maybe some of you have ideas. So maybe we can start to go from here with what comes next. And I guess the next thing that's on my mind is figuring out this cycle handling, extending this form of cycles to handle fixed point iteration and other kinds of recovery where you're not just reporting an error, you're actually expecting cycles to happen. That's part of the computation, which happens a lot in Rust-C. And my hope is that actually we can improve Rust-C itself, because right now, what I've noticed in working on the compiler is that there's a lot of cases where we have to work pretty hard to avoid cycles, and it's not really a good reason for it. It kind of makes you bend over backwards. And so if we could come up with better mechanisms to move that into the framework, I think that would be cool. But more on that another time. Any final questions while you have me on the phone?
Well, if you have some extra minutes, I wouldn't mind hearing your thoughts on the entity system. You had mentioned, I had briefly skimmed the Dada code base and the entity system that was baked into that.
Yes.
be interested in hearing more about it.
Okay. Well, I can talk about that for a bit, but before I do, is there any more questions on cycle handling? Okay. Yeah, the entity system. I'm pretty excited about it. It came out of some brainstorming from Alexi and I don't remember who else, maybe Lucas. Some other people were there. But the idea is that a lot of times, let's do this. A lot of times when you're writing Salsa programs, what you kind of want to do is process a bunch of data and then generate like results from that data that then are going to get further processed, right? So that's really generic. Let me try to make it a little more specific. If you were writing a simple compiler, let me go to example. You might parse the input program and emit a set of items that are like, first there's a class, then there's a function, then there's a class, then there's another function, another function, right? And then you're going to have other processing in the system that just looks at one of those things at a time, just looks at that first function. This is really common and extremely awkward to model in Salsa today, ironically, because what you wind up needing to do is you have sort of one query that generates, like, let's see. So let's start writing down. So silly compiler says parser of input text goes to a vec of items where an item is like a class or a function or something, right? And then you'll wind up with a query that's like parse file to vec of item. And the problem with that query is that anytime anything in that file changes, its result changes. So that means it's going to re-execute. That in and of itself isn't a problem because parsing is cheap in theory. Is this RFC the current idea? I think it's close to the current idea, yes. I think it's evolved. Well, no, it's probably not. I think it evolved a lot, actually. Yeah, it's not too far off. It evolved some, but it's at the right high-level details. So so you're going to parse into the vec of item, and now you're kind of in this annoying place because anything, it's not so much that you have to re-execute the parsing that's a problem, as if you were to say process an item and it calls parse file, now it's going to be dirty. And that means if you're not careful, kind of all of your compiler winds up re-executing every time anything changes, which defeats the whole point. So what you could have done in today's system is then you would have like get item I that calls parse file and returns item I, and then you have process item I that calls get item I. And now if the first, if one of the items changes but not the others, then you're going to re-execute get item all the time, but that's very cheap. That's just doing like a clone. So that's okay. So you can do it like this, but it's kind of strange and easy to get wrong. Like you might accidentally have had process item call parse file of I. This is very wrong, right? And you have to do all this cloning, which is not great. So the new entity system works differently. So this is old system. New system. In the entity system, what happens is the parser, we're going to declare an entity item, and it has some fields in it, whatever it is, class or function. And the parser allocates items by doing item new database and some data. And so when you declare the item, you also give its fields. Or actually, no, sorry. You give the values. When you call item new, you give the values for each of those fields. And what this returns an item, just like before, but an item is just an integer new type. And so it's kind of a unique ID. And then, so when I return the vec of items, I'm really just returning a vector of IDs. And then later, now for get item, well, you won't even need this get item function. But now I might have some code that does like process item, but instead of identifying the item by its index in this vector, which is awkward and not great, I will have it take an item. So it's going to take one of the items from inside this vector. And then it could do like item.field1 data. So all the fields of the item, it can kind of treat it as if it were a struct, except that to get its data, I have to call field1 or field2 or whatever, right? And so then maybe somewhere there's a loop. Actually, I kind of left that out of this whole thing. There must be somewhere a process all items that was going to say, let p equals parse file dot len for I in 0 to p, get process item I or something. That's what we were doing before. That's not very good, but it did have the advantage that at least, you know, if one item changes, the things that came before it these are cached still. But now what that looks like in the new entity system is just for item in parser, process item. And this is both simpler, like this kind of reads, if you think about what would you have done if you weren't using Salsa, it would have looked a lot like this. The main difference would be instead of calling item new and having a DB argument, well, you might not have had a DB argument. That's pretty much the only difference. You would have allocated your structs with struct new, stuck them in a vector, iterated over them. And then, okay, instead of calling field1 like that, you would have just said item.field1. A little simpler, but same basic idea. And only what's happening now is with Salsa, we're gonna get the reuse. And so to step back 1 second, what's gonna happen in revision 1 is we're gonna execute all the things, but in revision 2, what will happen? Well, when you call item new DB data, it's actually gonna look at the data that you're supplying and see in the last revision, you created an item and it had some data. And in the new revision, we're creating the same item, but with different data, then this item has changed. But if you create the same item, but the data is the same as the last time, it hasn't, right? So in some sense, the graph becomes like, you have the parser query, which returns a vec of items, but it has a dependency on an entity, or each entity that it creates. And those entities themselves can record, they each have fields like data, and they can sort of record when this field last changed. And so now my process item, there might be a dependency, which order am I doing my dependencies? I guess like this. So you have it, you end up with an edge like this saying, this entity was created by this query. And then process item for item 0 would have an edge. Actually, it's not really an edge on the entity, it's actually an edge on the field itself. So we can see which entities did you read and which fields did you use, right? And now if I reparse and I recreate this entity, but with the same data as last time, I don't need to re-execute this. That's the entity system in a nutshell. I skipped over a bunch of stuff, but I think what's really appealing to me about it is that it, along with a few other changes, lets you take the same code you would have written before and just kind of tweak it to pass the database argument around and call some methods instead of fields. And now it's incremental instead of being non-incremental, which I think is cool. It's a much more natural pattern.
Makes sense. I think it's probably one of the things we've struggled with the most when doing our redoing our code in Salsa, like this perpetual juggling of sort of methods and IDs to accommodate the incremental query structure.
Yes. Yeah, it can get pretty mind-boggling. The ability for, like, essentially what it enables, right, is that a query can have many outputs, because you can allocate, you have your main output, but then you allocate a whole bunch of entities, and those are all kind of sub outputs that have their own revision tracking. And that's just what you want most of the time, it turns out. There's a few
How
other.
far along is this?
It
Is
works.
this,
It's all implemented. There is one crucial bug that I found that I have to fix at some point. It's not necessarily implemented extremely efficiently. So there's two problems. First of all, I noticed that although in theory it's all implemented, in practice, if you ever actually use it, there's a cycle that arises where, because of the way I set it up, I think that you end up with a dependency cycle like this in a very trivial way, which I have to fix. I just haven't gotten around to that. But then the other problem is the way that I implemented it is that every field of an entity is its own query, which isn't really what you want. It was the easiest thing to do when I was playing with it, but it means you get like a lot more hash maps and stuff than you really need. I think you probably want just one hash map for the entity. And so there's some improvements to be made there. The other thing, let me think, was there anything else about the model? Oh, well, there's another really big advantage of this model that is not implemented yet, which has to do with memory management. But apart from that, it should be implemented and working. The memory managed thing is that you have another nice side effect of this model is if in the old Salsa model, right, the inputs were like integers or random things. It was not very clear where they came from. So I couldn't necessarily, let's say that I parsed in revision 1 and I had 3 items, and then in revision 2, I only have 2 items. I can't get rid of all the cache queries that relate to that 3rd item because they just look like queries on the number 3. And for all I know, that's a perfectly valid query to repeat later on, right? There's no way for me to know where that number 3 came from. But with entities, they are not forgeable, at least in theory. So like every time you call item new, you sort of get back an ID that the system gets to pick what it is. So that means if we execute the parser, or that the only place the user could have gotten an entity ID is by executing the parser query. So if we execute it again, and it doesn't create the same set of entities, maybe it creates a smaller set of entities, then everything that didn't get created is garbage and could never be accessed by the user, because anything that could have accessed it must have gotten that from the parser, and therefore it's dirty. And when you re-execute it, it can't possibly get it again because it didn't get created this time. So you get to go and do a bunch of cleanup kind of eagerly, right? Which is really cool. That I haven't implemented at all, but I like the idea of it. And I think it may just, it probably doesn't completely replace the LRU system we have, but it certainly augments it.
Awesome.
So I guess, yeah, I'd like to just land this. The only thing blocking it is A, I want to figure out why Rust Analyzer is slower, and B, well, there's the cycle bug. So I guess that's another good set of work items, is to start trying to land this, and I guess see that it probably wants to be optimized. But what would be nice would be to land it and start optimizing it in place. Like that would be a great opportunity for people to start taking the code into their own hands.
So
It's
this,
design, sorry.
oh, I was just gonna ask, this then depends on that, the slot no more changes that had that slowdown.
Yeah, I implemented it all on top of that because I forget why, but at some point I was trying not to, but at some point it became necessary. There's a few there's a few other details I didn't say. That one of them is really nice. There's another another really nice system. And this, I think, is why it depended on the slot no more. In the old Salsa, you could never get a reference into the database, so everything had to be clonable. But with the slot no more branch, we can do a little better than that. And what we can do is say, if we can, because every cached value is in an arc somewhere, let me think how this works. We can give you, we give you a reference into the arc to the data, so you get a pointer right into the database. And because it's immutable, that's what it is. Like in the old system, we would overwrite it sometimes if we recomputed it. We would overwrite the contents of the arc with a new value. But in the new system, we just make a new arc. So even if it gets dropped or like LRU'd or something like that, we still can keep the pointer valid. So I forget exactly how this works. I have to go look at the code, but somehow or other, we allow you to get pointers into the database, which means that you can have queries and entity fields that have regular old Rust types like vec or string, and they just work. Like, you return a vec and then you get back an ampersand vec when you're done with the query, and you can iterate over it just like any other vec. So that's another, like, I guess these are all different ways that the entity system aims to make Salsa code just feel a lot more like Rust code with some database parameter that gets threaded around. But that was the dependency that made me take slot no more, was I really wanted that. And to make that work, you need the whole idea of an arc that never changes its field. So I guess, yeah, now I'm debating, but I guess another good topic would be to sort of walk through some of that entity code, maybe try to pull it into a PR and do another group review, something like that.
Yeah, sounds good.
All right, see you all later.
All right. Thank you so much.
Thanks.
Yeah, thanks.
Thanks.
Talk to you later.